Okay, let's get started. So we're in lab three-phase power, and the goals of this lab is really to analyze three-phase circuits, balance three-phase circuits, and then figure out if our square to three stuff is correct, if our Y delta stuff is correct, if our assumptions about being in a Y or being in a delta, if our phase quantities are the same, or if our line quantities are the same, and just generally get a sense of how we can configure three-phase circuits. So interestingly enough, in a three-phase system, if you have a physical machine, so you have a magnetic machine and you want to produce a three-phase set of voltages or currents, you actually can just take one sort of north-south here. You can see this is the magnetic material, and it doesn't care the rotation. It's just that as this passes in phase one, you're going to get a peak value and a negative peak as the north and the south change. And that's going to happen 120 degrees behind or ahead of phase two, which is going to happen ahead or behind of phase three. So the way that you get 120 degrees of electrical separation in a really simple physical world is you just physically rotate the windings and space them out the equivalent of 120 degrees. So that's what AC machines are constructed on. We'll actually look how we have to modify this as we increase the number of magnetic poles on our circuit. We can change the speed a little bit and thereby change the phase relationship between these two, but we get a pretty good result. So we're going to go ahead and space things. And the other thing too is we want to make sure that we have a three-phase system, which is going to allow us to have a potential difference between phase A, B, and C. All those should have a potential difference. Now, if they were all exactly in phase with each other, then EA and EB and EC would all be on top of each other. Well, how do you get a potential difference? Because at any moment in time, I see that EA has a difference in potential with both EB and EC, right? A potential difference is just measuring the difference between two voltages. So this minus this, you can see, is going to be a delta voltage there. Now you can say, hey, wait a minute, Paul, what about EB and EC? They're at the same time. Well, if I continue the sine wave, my EC one is going down and my EB is going up. So I am going to get a potential difference. So over one complete sine wave, I end up having that potential difference. So that's another thing that's really important about making sure that you've got 120 degrees of separation between the elements so that you get some sort of potential difference. If you just want a potential difference, it doesn't actually have to be 120 degrees. It can be a different angle, but we talked about this in class. The reason why we pick 120 is because at all cases and times, the average value over one sine wave between EA and EB is the same as EB and EC, which is the same as EC and EA. So when we talk about a balanced system, we can see how all the magnitudes of the voltages are the same. And that's a hugely helpful thing for us to analyze systems and work on them because we don't have to keep track of which one's phase A, which one's phase B, and which one is phase C. So what we have is a three-phase supply. So we have three power supplies, three independent power supplies, and we reference those to each other, and it can be a common neutral point. So we have, in this case over here on the left, we have a Y-connected system and a delta-connected system, and this can apply to either the source or the load. We can have a source, so we just would substitute a power supply here and here. Or if it's a load, we just show our impedances here. So when we talk about a three-phase system is three independent elements. So in this case, we have three, we'll show these as inductors, and we just connect them in a manner so that we have all, so that they reference to a common point. Same thing with a delta. In a delta, we do this tip-to-tail fashion. And we end up with three independent loads, completely independent, have nothing to do with each other. And it's only when we interconnect them at common points is when we can apply a three-phase voltage and we can get good results. So a couple things. We can see that a phase voltage is always the voltage drop across a single element. And the line voltage is always the voltage drop between the incoming lines or outgoing lines if it's a source of your supply or load. So here I can see that this is E phase, which matches my E phase across here. This is the element of interest, this inductor here, which is going to be the same as this element here. So the phase voltages are the same. But now if I look at the line voltage, which is across any two lines, Now I've got two voltages, a drop here and a drop here. And since this is a potential difference, it's plus and minus, I would subtract the A voltage from the V voltage, and then I get VAB. In a delta, if I subtract VA minus VB, that is exactly the same as the phase voltage. So in a delta, the two are the same. In a Y, the voltages are different, and they are offset by the square root of 3. So the square root of 3 is always the case for every balanced system, and you can see that here. Now, if we talk about a current, the current is going to be the opposite. So the current that we see is in a Y-connected load. We can see that our line current, this is the wire that connects the power supply to the load. Our line current is just the current that goes in the interconnecting line between the two. Our phase current is the current that actually goes through the elements or element of interest. So we can see that our phase current and our line current in a Y-connected circuit are the same. In a delta connected circuit, our line current is what's going between the line, but my phase current is in this resistor here. I have this current here, and then by the way, I also have this current, whereas my KCL is done at this node. So I have this current plus this current plus this current, which are the sum of the currents in that node. So in this case, our line current does not match our phase current. The difference here is that we have our square root of 3. So in Y-connected circuits, I line is I phase. And in delta connected circuits, you have a square root of 3 multiplier. In Y-connected circuits, my line voltage is square root of 3 times my phase voltage. And in delta connected circuits, they're the same. So it's important that we keep track of those throughout the slab, because you're going to be looking at a number of different circuits and being able to ascertain how to go ahead and compare and look at things. So the first thing we're going to do is set up a circuit here. And this is going to be a Y-connected load. Now, our power supply is going to be connected in a Y. And the reason why is because you notice this neutral here. In delta, you don't have a neutral. So my power supply is always going to be a Y, and then my load is going to be Y or delta, depending on the configuration. And so I've got this circuit set up here. And what I've done is I've actually done this first circuit for you. So I will help you with the first circuit, and then you can help yourselves. Tell me when you can see my actual circuit.
I can see it right now.
Okay. So all I've done is the convention we adopted sort of the last lab. I've got my terminals 4, 5, and 6. This is my neutral. I go red, black for my currents, my ammeters. I do red, black for my voltmeters. And I do top and bottom for my resistors. And what I do is I do my connection here. And then because this is a Y-connected load, I take all 3 of those resistors and place them in a Y configuration. I want to just confirm that my neutral current is 0, which is should be approximately equal to 0 in a Y-connected circuit that has a balanced voltage and has a balanced load. If that's not equal to 0, then it's not necessarily a balanced system. So I'm only adding this meter in here to sort of confirm what we discussed during class. So here is our circuit diagram, and I'm going to scooch this over just a little bit so that hopefully you can see the whole thing. And now what I'm going to do is bring this over. Well, let me get this out of the way. And here is how I set up my lab volt station. I went ahead and included the capacitor module. You actually don't need it. Unknown error equations. Weird. I don't actually need my capacitor load as of yet. But what I do need is my resistor load and my module here, and then my power supply over here. So we have to turn that on, and then we're going to flip our power supply. And again, I'm going to give you an opportunity to do this. And I'm going to turn it up. So the description is turn it up so that the voltage between terminals 4 and 5 is approximately 208 volts. So I'm going to just toggle on a meter here. And measure terminals 4 to 5. So here's 4, and it doesn't necessarily matter the polarity. I thought I had the power supply off, but okay. And now I flip this into the on position. So I've got my voltage configured over there. The voltmeter is acting a little funky today. Sorry about this, folks. Let's turn it off and then try it again. There. All right, so I'm going to do that, but simultaneously with that, for good practice, what I'm going to do is I'm also going to bring these up over here. So as I'm turning this up, I'm going to see if my voltages and my currents go up correspondingly. So I turn this up. I got to make sure I'm on continuous refresh. Turn this up, and I can see that all these currents are going up slowly, and my voltage is going up slowly. And why does the 43 volts not equal the 24.88? Why aren't they the same? Well, if I look at my voltage here, I'm looking across the phase voltage, which is the individual phase from phase to neutral here. This is from 4 to 5, which is across terminal 4 to 5. So they shouldn't be the same. In fact, if you multiply 24.88 by square root of 3, you should end up with something around 43. So I'm going to bring this all the way up to 208 volts, which is almost all the way on. Close enough for me. And here are my values for voltage, current, and I also have my power through here. And I'm not actually asking you to get the power. You will need to do that next in the next step. So there. So I'm going to pause here. I'll pause the video, see if let me ask if there are any questions. And if there are no questions, I'm going to pause the video and I'm going to give you an opportunity to build your circuit. So any questions on this first step? All right, with no questions, I'll bring this circuit up. I'm going to pause the recording and give you all, let's see, it's 1:10. How about 5 minutes to wire the circuit up and then see if you can get the results consistent with what I got. Does that work for everybody?
Yep.
Okay, so pausing the recording here. And I'll give you 5 minutes. So 1:15, here we go. Okay, how's everybody doing? Did everybody get to this point in their lab, or they get the similar data, or are they still working on it?
I'm still working on it, but I'm almost done.
Yeah, same
Okay.
here.
All right, you need another minute or two?
Oh yeah, another minute's good, thanks.
Okay, we'll do 1 more minute. It's hard when there's no cameras on. I can't really tell what people are looking and what they're doing, so.
Paul, do you have that multimeter hooked up just directly line to line on the power supply? Is that what you have?
Yeah, I go from terminal 4 to 5 just to measure the 208 volts. You actually could, if you could zoom in enough, if you switch this one to 4 to 5, you might be able to see it, but I can't see it. So I just go ahead and use it that way. Okay, how about now? We good? It's been a couple minutes.
Yeah.
Okay, like I said, I can't really tell because people's cameras aren't on, so very difficult for me to tell. All right, so hopefully you got that data, and then you can go in and fill in the blanks and all that stuff. But the key important thing is are the load currents and load voltage is about the same. So the magnitudes is all should be about the same. That's the concept there. And then the other thing is, are the currents there, get this out of the way, you can't see, are the currents, the phase currents and the line currents should be the same. And we'll see when we look at the next part, we're going to go ahead and get the results. So your phase current should be the line current, which is the same values that you calculated. So the average current there is just taking the 3 and then dividing by, adding the 3 up and then dividing by 3. And then you should get the same results. Also the power, because this is purely a resistive load, you can see that the powers are all about the same. But you can also, if you want, you can turn on this third meter and you can sum the 3 here with this button here. You click OK, you turn it on, and then you get about 140 or so, which is about the sum. And that should be pretty close to 3 equals V time I. It may not be exact because remember, no resistor is purely resistive. So you might have a slight difference in what the actual power is versus what you're getting over here, but you get the idea. Any questions on the first part of the lab? Can we proceed on to part 2?
Yeah.
Anybody, any no's? How's about that? Remember, I can't see anybody's faces. I can't see your workstation. So I'm really relying on you all to indicate if you're ready to continue or not.
Paul, what do you mean by part 2 exactly?
The next part where we're switching to a delta connected load.
Okay.
One person in the chat. All good to keep going. Okay, we'll keep going since I hear no nays. Thanks, Taylor. All right, so best way to do this one, in my opinion, is we're going to start pretty much with the wiring from scratch because you can see I've got, I don't know, 20 or so odd wires here. So my suggestion is you just delete every wire. Except for our power supply wire for the DAC. And now this is what's a little bit more difficult about this lab is I want to come out of 4 and I want to run my current only through my R1 resistor here. I want to measure the current through the R1 resistor. So if I just did this, if I went from there to here, and then went from here to here to my resistor, and then I also see that I'm coming out of the bottom of this resistor, if I just connected it like that, I would have a problem, right? Because the current that I'm measuring here is the sum of the current here plus whatever is going to be going over here. So this one, we got to think a little bit about it, and we're going to mix it up. So we're going to come out of terminal 4 because we got to get power. We're going to go into our resistor. Now, one thing I'm going to do with my resistor is I'm going to go ahead and connect this in a delta. So my delta is going to be here to here, here to here. And I'm not going to close this delta yet because I don't want this wire to contain any current from here. So what I'm going to do is I'm actually going to drag that current up and over to 4. So this current is only the current through the resistor. It doesn't include any current going through here. It's basically a bypass that I have. So what I've done is I've come out of 4, and this is where you got to be careful. I come in to the top of I1, and I went to the bottom here of this one. But this is a completely separate wire. This is where it gets a little more difficult to show this. So you want to show that this wire here actually kind of bypasses it, jumpers all the way over to this terminal and not over here. Okay. I'm going to do the same thing for the next one. So I'm going to run my current here. And I'm going to run my current here. Now, the problem is you can see I've got this wire over here. Let's see. Do I have a problem yet? Yeah, the problem is right here, right? You can see I've got this terminal. So I don't want to include this current over here. So I see that this runs directly into this terminal 5. So I'm actually going to pull that all the way back here. So again, I'm sort of bypassing this resistor connection and not including it in the circuit. So it kind of looks like it's open. Oh, wait a minute. I gotta go here. Sorry about that. I gotta go to the bottom of that terminal because if you can look over here, if I follow this along, this one already connects to terminal 5. This one doesn't. So this is where it gets a little squirrely because you can say, hey, wait a minute, Paul, how is this working? Well, I'm at the bottom of R1 and I'm measuring the current I'm connecting the bottom over here, but I'm also doing this one, which goes directly into here. So essentially what I'm doing is I'm forcing it just to measure the current through R2. It's a little squirrely, but it does the trick. And then the other one I've got to do is here, terminal 6. And then I got to do this one again over here. But what I'm going to do is I've got to take this wire, right, that's coming on the bottom, and I'm going to run it directly over to there. Okay. And now I'm going to go ahead and measure the voltage across E1. So this one's pretty easy. I just go from here to here. Move these out of the way. Here to here. Oh, sorry about that. Really tricky where you grab these. And let me just make sure that I have this one correct. Yes, I'm good to go. And then lastly, I go from here to here. Now, I've got my circuit all wired up just to measure the currents going into my resistors, my individual resistors. I also need to make sure that the voltage drop across each one of these resistors is only 120 volts. So what I'm going to do is I'm actually going to measure directly across one of the resistors here. And I'm going to turn that up until I go to 120 volts. Anybody want to guess why I'm limiting that to 120 volts? If you look at the 300 ohm resistor, what's the rating on the 300 ohm resistor in terms of its current? Anybody read that? I can't read it on my screen, but hopefully you can zoom in on yours while you're building your own circuits.
Is it 0.4 amps?
Very good. It's 0.4 amps. What is 120 divided by 300? It's 0.4 amps, right? So the reason why I don't want to drive this more than 120 volts is I don't want to exceed the capacity of these resistors. So now I'm going to flip the switch. I'm going to look over here, make sure things turn up the way I expect them to. All these currents are about the same. All these voltages are about the same. So I'm feeling pretty good. I haven't exceeded 120, so I can turn this up. So everybody check what I'm doing. I'm going up slowly initially just to see that it's working okay. And then once I get it working okay, I'm feeling pretty good. I go from there. And as we said, we don't really want to exceed 120 volts. We're a little bit over. So we can see our voltages are a little bit higher here. And for some reason, this voltage here is, let me just delete this and see if that makes a difference. Offs for some reason by, oh, I think I know why. No, I don't, not the case. I'm not sure why this last one is slightly different. You can see it's off by, like the voltage is E3. So that's there, that's there. Let me just make sure I have my current set correctly. Yeah. I'm not exactly sure why. I am returning this. to terminal 6. So I don't know, maybe that's just the software. I mean, it's only up by 6 milliamps, but you can see it's giving a different voltage. So that is the second part of the lab. So I'll give you, it's 1:27. Is 5 minutes enough to go ahead and build these circuits, or do you need a little more time to do that?
Take a bit more time.
Okay. How about 7 or 8 minutes? I mean, I also don't want to go too long because people are going to start falling asleep. So how about it's 1:27 now? We'll try checking in at 1:34 and see where we're at. Does that work for everybody?
Yeah.
Okay. I'm going to pause the recording. I'll keep my power supply on. Unless there's any questions, I can answer questions. My intention was to put the circuit up over here. Again, you're just doing this bypass thing over here. So the way that I would show this in the circuit, I would actually show it as, let me show the wires here. I guess this is one erase without doing it. So let's erase it this way. So I'm going to delete, I'm going to run this wire directly out of terminal 4 and go through there. And then what I did is I ran this wire here, this B, I also ran that directly to terminal 4. I delete that out. Then I go through the rest and of the circuit as shown. Over here, I go directly, whoops, directly out of that one. So that gives me to my I2 here. And then let's see, where is the other? Oh, and then this one I also go directly over to the resistor here. So that's where it gets a little squirrely, is where you have this disconnection here. So you're going to run one wire, same thing over here. You're going to run that back to the resistor. And then you're also going to run this thing all the way back over here. So you're just getting the current going through. And oh, by the way, this current source should be down on the side. All right, so actually it's now 1:29. I'll give you to 1:36, give or take, and we'll go from there. So let me pause the recording, and you can do your magic. Okay, hopefully that was enough time for everybody to record your results. The key thing is that when you looked at this part, okay, so you got all your data, hopefully you recorded it, the load should be balanced, and your average phase current should be a certain value. And what you'll notice is the phase voltage, the voltage that is across the resistor, is exactly the same. So you get exactly the same current, whether it's Y or delta. So in this case, what we're seeing is what's happening with our circuit elements and what is our phase voltages and phase currents in a Y or a delta, are they the same thing? So now we have to modify the circuit. So let's go ahead and turn this off. So now we have to adjust the circuit. So I'll just erase it off. I'll just do it like this quickly. Now we have to go ahead. Whoops. And we have to modify the circuit. So now we actually want to measure the actual line currents. So this case, the modification is we're essentially going to go ahead and simplify our circuit down. So we're just measuring these currents over here. So these are completely out of the picture at this point. So all we have to do is do a standard delta. This is a much easier circuit to lay out. And we can build this circuit here. I don't know if it's doing that. I might have to hide this. Okay. I'm not sure why this doesn't want to hide. I don't know. I can't get this thing to move out of the way. So let me put back maybe. Okay. Well, It's gonna make it. So let's see if I can move it up. All right, it's gone now. So all we need to do to modify this, and again, it's probably easier just to start back over again, and we're just measuring the line currents. So I'm going to go ahead and turn that off and delete every one of these wires. So I have a much simpler circuit. I'm not going to change that voltage knob because hopefully I can make a pretty simple change from one circuit to the next without having too many problems and having any wiring mistakes. So I'm just going to set this up as a delta. So I'm going to go from here. Actually, let me just do it over here. This is my standard delta configuration. I'm going to make it as consistent as possible. So here's in a delta. I go tip to tail, and then back through here. Now all I need to do is run my currents through that leg. Whoops. Then I got to do another one here. And here. And the last one will be from 6 over to here. Now, I can certainly measure the voltage across any one resistor. So let's do that. And I should get the same voltage. And now I'm going to flip this on. And all I'm looking for is my currents. I actually don't care about any of the parameters because nothing else should have changed, right? I don't have to. Wow, can I auto? I might have to quit whiteboard because it's not letting me rescale anything. It's like it's in a lost. Yeah, I think I'm gonna have to restart whiteboard, but you can see that all my currents are now around 0.7 essentially. So this is the line current going into the delta, where the previous one I was getting the phase current. So based on those values, you should have an average line current from this part, and the previous part, you have an average phase current. Now, what is interesting about that ratio? Do you have any idea? What is interesting about measuring that value? How does this current here, the 0.707, compare to the current that we had in the previous circuit?
It's pretty much square root of 3.
Yeah, it's the square root of 3 difference. So in a delta, what we see is that the voltage across, the current across the current into the phase current is square root of 3 different than the current that's into the line. And it's exactly what we'd expect it to be. So it's almost exactly square root of 3. So now let's go ahead and tweak this circuit a little more. So again, turn it off. And all I'm going to do now is measure the voltage across each of the resistors. So hopefully this is pretty easy. I just come in and I measure the top of this resistor, bottom of this resistor, move some lines out of the way because that's just what it takes here. Top of this resistor, bottom of this resistor. Got to be really precise. And then lastly, top of this resistor, bottom of this resistor. So now when I turn on my power supply, I'm measuring the same voltages I measured before because the line and the phase voltages are the same, right? I'm just looking across the top and the bottom, which is the phase. And now I've got my voltages, my currents, and now I can calculate my power. So it's not this times this, it is this voltage times the 400 milliamps that we did before. Same thing here and here. And that's what I get for my powers over here. So I'm going to pause for 5 minutes and give you all the opportunity to go ahead and set your circuit up. So again, just follow through with the delta, measure the line currents going in. And let me put this up over here so you can see. Sorry that I had to kill whiteboard, but it wasn't working. So let's paste that here. And now my circuit becomes 4, 5, and 6. This is R, 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 oops, R, B, 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 RB, RB. It's important to make sure that you have the R and the B over here. This is top and bottom, top and bottom, top and bottom. So just be careful on this side over here because you have to swap things around. All right, so I'll give you to 150 to be able to do this portion, unless anybody has any questions. I'm still sharing my screen, I hope, right? Doesn't show me right now, but let me just make sure. Share screen too.
Yeah, you're still sharing your screen.
Okay, because normally it's a little, but it's just a metering screen, right? So is that correct? You see the metering results and you see whiteboard?
I see whiteboard in front of the metering results, but I do see some of the metering results,
Yeah, sorry, I can't.
all the power results.
Doesn't seem to be allowing me to resize whiteboard. I'm not sure why. I don't know. I'm not sure. I don't think it's like its whiteboard is lost. Normally I should be able to resize this, and let me try over here. There we go. Yeah. Gotta be really particular. So there. All right, so I'll give you a 150 to get this one done. So I'm going to pause the recording. Go from there. Okay. How'd that go? Anybody have any questions or any struggles with this part? Are you still working on it, or are you ready to move on to measuring power in a three-phase circuit? Remember, I can't see your work, so you need to give me some sort of an inclination or indication of what you need help on. If you don't need any, we'll just
Had
continue.
issues, but I figured them out, Paul.
Okay. Did you get all your data collected and you're ready to?
Yep.
Okay. Anybody else having any issues or ready to move on?
I'm good to move on.
I'm good as
Yeah,
well.
I'm just answering some of the calculation
set.
questions, but we can move on.
Okay. All right. Let's move on to the next part. So I'm just going to copy this in. So now we're actually going to do a three-phase load with some resistance and some capacitance in. So here's one thing to be careful of. The resistor and the capacitor here are connected in series first, then you connect it in a Y. So you have a neutral here. Don't put these two, don't put a neutral between these two resistors. You've got to go ahead and set them up. And then otherwise than that, we're just going to calculate line currents and the phase voltages, because line currents are the same as phase currents in a Y, and phase voltages are going to give us the actual voltage drop across the series resistor and capacitor combination. So we're going to go ahead and start doing our terminals. This is red, black, red, black, red, black, red, black here as well, here as well, here as well. And then this is just top and bottom, just the whole way through. Really kind of very consistent story. And then again, you can see that that last wire going back to the neutral is all set. So turned everything off, and then I'm just going to delete like crazy because I'm not going to start anywhere here. It gets too busy. It's too messy. If you were out in the lab and I try to do this stuff, you would see it's just almost impossible to do any connections. So it's usually much better to just start from scratch, and then you can see your wiring. Now, one of the things I will say is because we have a load already set up here with our series load, my suggestion is just go ahead and connect these in series. First, so you can see the resistors are connected in series, and then this is my neutral connection that I connect over here. So I have my individual resistor sort of connected in series with my capacitor, And then all I need to do is run that back to my neutral, which is way at the bottom of the capacitor. Don't put that at the bottom of the resistor. Make sure you identify that as going to the bottom of the capacitor. Now I'm going to take my incoming currents and I'm going to go to the tops of the resistors. So what I'm doing here too, and hopefully you all are sort of picking up on this, I'm trying to be very consistent with how I lay my wiring out. And what I mean by that is I want you to see how each one of these, the way I connect my resistors and my capacitors, it's the same, whether it's bank 1, bank 2, or bank 3. It's always configured exactly the same. There's no differentiation. So it makes it just easier to troubleshoot and easier to check. And hopefully it helps make sense in terms of laying out your circuit. So I've got my 3 currents all ready to go and measured. Now the only thing I need to do is measure my voltages. And you can see I'm just checking across the resistor and neutral, or the resistor and the capacitor combination. So I'm going to run over here. That's my first. Oops. My second is here, that one resistor, and this one over here. So again, just trying to be consistent. And then my last one, I've got to move some wires out of the way. And I'm going to run to this resistor top. Oops, didn't like that. I guess I did a bad job of connecting it. And to the bottom of this capacitor. Now I have to turn on 600 ohms of resistance. My wires are so messy I can't even reach the toggle switches. And 1200 ohms of capacitance. And so now I'm going to be able to apply my forward and neutral voltage. So I'm going to set this up, measure my voltage here, and here. And what I'm going to measure is I'm going to measure the voltages. But the first step I need to do is it says solve the circuit to determine the following parameters: active power, reactive power, and apparent power for each circuit. So let's bring up whiteboard. And if I look at the circuit, right, I can basically redraw that to say I've got this, and then I have a resistor, a capacitor, resistor, capacitor, resistor. And this, kind of looks messy, is how my circuit's going to be. Well, recall, if I have this neutral going over here, that neutral doesn't even matter. But it makes things easier because this individual circuit here is one phase of that power supply, or one phase of that circuit. That's 120 volts. This is 600 ohm. This is minus J, 1200 ohms. So if I can calculate the current through here, I, which is equal to 120 at an angle of 0. We picked at an angle of 0 because that's our reference. We divide that by 600 minus J 1200. And then I'm going to go ahead and calculate a current. I'm going to show you all how to do that in MATLAB because I really think MATLAB is really powerful tool. But my current I is equal to 120 at an angle of 0 is just 120. Then I'm going to divide that by 600 minus J times 1200. Now it's going to display thing in rectangular coordinates. So I just use this display vector. So that's going to be the equal to the absolute value of I and the angle of I times 180 over 180, not 10, over pi. Okay, so I have my angle and my absolute value, and this is what the current magnitude and angle is going to be. Did I forget? Oh, I got an extra parentheses here. I don't need this parenthesis. So that tells me I have I equals 89.4 at an angle of 63.4. And this is in milliamps, right? Yep, so it's in milliamps. So now the first question is that current what I expect it to be? Really. Whiteboard is really acting funky. Is this current what you expect it to be? Well, I don't know what the magnitude of current, but I know that if I have 1200 over here, I know that my 120 is going to be divided by a number at least 1200 in magnitude, right? It's going to be at least 1200. So I know that I'm going to get at least greater than a tenth or less than a tenth of an amp. So that's 100 milliamps. So I'm not too far from that. So I'm feeling pretty good about the magnitude. The other thing, which is more important, is can you tell me anything about this angle theta here? What is significant or important about that angle theta? And is that what we expect it to be? Remember our Eli friend. What does Eli say? It's not a trick question. Anybody? If I have a resistive capacitive circuit, what does Eli tell me about anything? Nobody wants to talk. I'm happy to randomly pick somebody.
The current would lead the voltage.
Yeah, current leads the voltage in a capacitive circuit. So my voltage here is 120 at an angle of 0. So this is V. My current is someplace over here. Does the current lead the voltage in this circuit? Sure it does. 63.4 is pretty good. So I'm feeling pretty good about it. So now all I need to do for one single phase circuit is S equals V times the conjugate of I. Now go back to MATLAB to do my calculation. So S equals V 120 at an angle of 0 times the conjugate of I. And I end up with 4.8 minus J 9.6. This is P for the resistor, and this is Q for capacitor 1. And we know when we have a phasor diagram that is over here, our power triangle, because we do S equals VI conjugate, is going to go down here. So we see that Q should in fact be a negative number. So we have our P and our Q calculation. And by the way, we know that this is S1. That's also got to be the same as S2, which is the same as S3, because if it's a balanced system, they all should be the same. And the S total is equal to 3 times P1 plus 3 times J Q1. So our total, let's see, 12, we have 14.4, give or take. And then we have minus, point right there. And then we have minus 28.8 times J. So these are our total P's and our total Q's for the circuit. So we have the individual ones, and then we have the total ones. So now we can go back to our circuit, and the voltage has to be 120 volts. So we're going to turn that all the way down again, just to be safe. Flip our switch, turn it up slowly, and then see, hey, our voltages look all about the same. Our currents look pretty good. So we're able to turn it up pretty quickly because we don't have anything that looks anything out of whack. I take it up to around 120. That's close enough for me. And what I end up with is, here are my voltages. Here's my current, which is good because if you remember, I calculated around 89 milliamps. And now we check our power, 4.57, whatever. I said 4.8, so not too bad. So 4.5, whatever, 4.5, 4.5. I said our total real power is 14.4. Now I'm going to check the Q. So click all three of those, and I can see that I said 9.6 negative. I'm not too far off, 9 point whatever. And then last thing I need to do is check my total. I said minus 28.8. That's minus 27.5. So reasonably close to the values that I would expect to have. And it's all based on doing my equivalent circuit and just showing this as a single phase equivalent. So once we have a three-phase circuit and it's balanced, you really can just do a single phase equivalent, and then you can do all the work kind of manually go from there. Okay, any questions on that?
Are you gonna want us to like turn in those hand calcs? What do we have to do
Yes.
for that?
Yes, please do the hand calcs, showing me the results, and then the actual data stuff. Yep. But hopefully you don't have to do this level of calculation. You could just say, hey, I know that I is going to be equal to V divided by Z. And then you've got your calculation there. And then you just say S equals BI conjugate. And then that ends up with P and Q. So you can just do that in your calculator. And then you can do the three-phase one just by multiplying the P and the Q by 3. And you got the answers. Okay, so shall I pause here, either with this element or with the circuit, or do you guys want this up right here? Which parts do you want? I can kind of put 2 out of 3, I think. Sort of. I don't have the total here, but I've got the rest of the stuff. Do you, which parts do you want me to leave up? Anybody? Well, since nobody's telling me, I'll just leave this up and I'll give you 7 minutes to do it. So it's 2:05 now. I'll give you to 2:12 and see what you get. So unless there's any questions, I will pause the recording. So one Taylor said the math, please. So how about I put this up over here like that? And if I zoom out just a wee bit, hopefully this is still legible and you can actually see the configuration of the circuit. Is that okay? Is that give enough information? You've got the wiring for the circuit here. You don't actually have the circuit, but I think I can bring this data meter up. And then you can see the actual data. Okay, so let's see if I can shrink this. Oh, boy. It just won't allow me to do it. I can do it on a different screen, but that doesn't really help me all that much. So if I can turn off some of the meter settings. Maybe the meter layout. All right, so I want 3 rows and I want 4 columns. Okay, hopefully. The only thing you won't be able to see is this. This is 120, but maybe I'll pull it up a little higher here. I think that's the best I can get you in terms of being able to see stuff. So you're missing just a little power triangle here. So I will draw that over here. Here's P. Here's Q. Here's S. All right, so that gets you the meeting results. You have the wiring here. You have the calculations. That should be enough to do it, but if not, we can always bring up the stuff. So again, I'll pause for 7 minutes. It'll be 2:14, and we'll go from there. Okay, we're back. How'd that go? Any questions? Anything confusing? Still working on it?
Yeah, could I just get a little, like, just a little bit, like 30 seconds, minute?
Yeah, let's do 2 minutes. That way you don't have to worry about it. So let's do another 2 minutes. And we'll check back in. So again, I'll pause the recording, give you 2 more minutes. Okay, it's been a couple minutes. I still need a little more time to work on this one. Oops.
I'm good.
You good? Okay. Anybody else?
Should be all set.
Okay. Well, I think that that's all I had for the part of the video where I was gonna do some explanations and working with you all. I'm gonna pause the recording again, and then I'll stick around as long as people need me to. Answer any questions. If you feel like you have enough information, feel free to drop off, and I will see you in class tomorrow. So I'm gonna stop, pause recording and answer questions if you have any.